Hello students, welcome to physics class. Today we discuss the phenomenon of self-induction and mutual induction. Let us see what is the phenomenon of self-induction. The phenomenon of production of induced EMF in a coil when a changing current passes through it is known as self-induction. Self-induction is the phenomenon of production of induced EMF in a coil when a changing current passes through it. For example, here see we have a coil which is connected in series with a battery and a tap key. Initially, if you are closing the switch by pressing this tap key, the current starts flowing. The circuit current or battery current is developing in this direction. Once the current start flowing through this coil, you know that every current carrying coil produce a magnetic field. So a magnetic flux or the magnetic flux associated with this coil changes. We know that whenever the magnetic flux linked with a coil changes, an induced EMF and an induced current is developed in that coil. So that induced EMF or induced current flows in a way that, in a direction that it opposes the development of the circuit current, just opposite direction of the battery current. So such an EMF is known as back EMF. Such an EMF is known as back EMF because it opposes the circuit EMF or it opposes the circuit current. And this phenomenon is known as the self-induction. Whenever the magnetic flux associated with the coil changes, an induced EMF develops in that coil itself, and that phenomenon is known as self-induction. Actually, when you are closing this switch, the magnetic flux associated with the coil changes. If the switch is closed for a long time, the flux remains same. The current is not changing, so flux remains same. So the no induced EMF and no induced current if the switch is closed for a long time. Suppose after that we are releasing the tap key. Once we are releasing the tap key, we are opening the switch. So what happened? The current flowing through the circuit stops suddenly. So the magnetic flux associated with the coil changes or it decreases. So by the same time, an induced current develops in this coil to increase the current in the direction of battery current in order to remain the or in order to oppose the flux change. So again we can say an induced EMF and induced current is developed in this coil when you are opening the switch. This phenomenon is known as the self-induction. So the self-induction is the phenomenon of production of induced EMF in a coil when a changing current passes through it. You know that when you are closing the switch or when you are opening the switch, the current through this coil changes. In both these cases, an induced current is developed in this coil just opposite direction of the changing current. And that phenomenon is known as self-induction. Now let us see what is the coefficient of self-induction. Suppose at any instant the magnetic flux phi linked with a coil is directly proportional to I. We know that suppose a current I is passing through a coil. This is a solenoid or a coil. I current is passing through this coil. We know that the magnetic field produced by this coil is equal to B is equal to mu 0 N into I. The magnetic field is directly proportional to current, or the magnetic flux produced or the magnetic flux associated with this coil is directly proportional to current. Phi is directly proportional to I. Or phi is equal to one proportionality constant into I. Phi is equal to L into I. And here this proportionality constant L is known as the coefficient of self-inductance. This proportionality constant L is known as coefficient of self-inductance. That is, if you are plotting a graph between the current passing through this coil and the flux associated with this coil, we will get a straight line. When I equal to 0, flux is equal to 0. When I increases, flux also increases. and see that the slope of this graph, actually if you are finding the slope of this graph theta, this is theta and tan theta, we are getting tan theta is equal to 5 by I. Tan theta is equal to 5 by I. So the flux is equal to, okay, flux is taken on y-axis, current is taken on x-axis, and if you are finding the tan theta, the slope of this graph, you are getting 5 by I. That is the self-inductance of that solenoid or self-inductance of that coil. Now let us see how can you define the self-inductance. In this equation 1, suppose if you are putting I equal to 1 ampere. Suppose 1 ampere current is passing through this coil. Then we can write phi is equal to N. When I equal to 1 ampere, phi is equal to N. So the self-inductance of a coil numerically equal to the flux linked with the coil when a unit current flows through it. When a unit current flows through it, flux is equal to self-inductance. So that's the definition of self-inductance. The self-inductance of a coil is numerically equal to the flux linked with the coil when a unit current flows through it. Now suppose if you are just differentiate these equations, we getting okay by E equal to minus d phi by dt. That is induced EMF is equal to the rate of change of flux, the time rate of change of flux. So E is equal to minus d phi by dt. Induced EMF developed in this coil whenever the flux associated with the coil changes. Now according to Faraday's law of electromagnetic induction, E is equal to minus d phi by dt. That's equal to substitute for phi. Phi is equal to L into I. So minus L into di by dt. Put it equation 2. So induced EMF is equal to the self-inductance of the coil into the time rate of change of current through that circuit. Minus L into di by dt. Now suppose if you put di by dt is equal to 1. Di by dt is equal to 1 in this equation 2. So you're getting E is equal to minus L. E is equal to minus L. See another definition for the self-inductance of a coil. The self-inductance of a coil may be defined as the induced EMF set up in the coil, because E equal to L. Induced EMF set up in the coil due to a unit rate of change of current in it. Suppose the current in this coil is changed at a rate of 1 ampere per second. That is di by dt is equal to 1 ampere per second. 1 ampere per second. Then equal to minus L. So the self-inductance is equal to induced EMF when di by dt is equal to 1. That's another definition. The self-inductance of a coil may be defined as the induced EMF set up in the coil due to a unit rate of change of current. Now see what is the SI unit of the self-inductance. The SI unit of self-inductance is, write an expression for L. L is equal to, rearrange this equation, L is equal to E divided by di by dt. L is equal to E divided by di by dt. Minus sign is the no problem. Okay, L is equal to E divided by di by dt. Now the unit of the unit of EMF is volt and di by dt ampere per second. Ampere per second. So we are getting 1 volt divided by 1 ampere second raised to minus 1, and this unit is commonly known as Henry. 1 volt divided by 1 ampere per second is commonly known as Henry, and it is denoted by a symbol capital H. Henry is the SI unit of self-inductance. Now let us see how can you define Henry. When will you say the self-inductance of a coil is 1 Henry? The self-inductance of a coil is said to be 1 Henry if an induced EMF of 1 volt is set up in it when a current in it changes at a rate of 1 ampere per second. You see that when E equal to 1 volt and di by dt is equal to 1 ampere per second, L is equal to 1 Henry. So that's the definition of 1 Henry. The self-inductance of a coil is said to be 1 Henry if an induced EMF of 1 volt is set up in when a current in it change at a rate of 1 ampere per second. If the current through a solenoid or a coil change at a rate of 1 ampere per second, if a 1 volt is induced in that coil, then we can say the self-inductance of that coil is 1 Henry. Now let us find an expression for the self-inductance of a long solenoid. Here we have a long solenoid. Suppose L is the length of this solenoid and area cross section is A. The number of turns per unit length of the solenoid is equal to N, is equal to total number of turns divided by L. Suppose it have a total N number of turns, and so the turns per unit length is small letter n is equal to capital N divided by L. When I current is passing through the solenoid, suppose I current is passing through the solenoid, a magnetic field produced by the solenoid, and this magnetic field is equal to B equal to mu 0 Ni. As it is a long solenoid, we have the magnetic field due to the solenoid is uniform and can write as B is equal to mu 0 Ni. Where mu 0 is the permeability of vacuum or free space, N is the turns per unit length, and I is the current through the solenoid. Suppose consider such a one turn of the solenoid and area of the turn is equal to A. So what is the magnetic flux linked with each turn of this solenoid? It have a total n number of turns. So the magnetic flux associated with each turn, if you consider a single turn, we can write as B into A, where B is the magnetic field and A is the area of that turn. You know the magnetic field is parallel to the length of the solenoid, or it is perpendicular to each turn. So we can directly write the magnetic flux associated with each turn is equal to B into A. That is equal to mu 0 Ni. This is B, mu 0 Ni into A. If R is the radius, we can write as mu 0 Ni into pi r square. So what is the magnetic flux linked with the entire solenoid? This is the flux of a single turn. So total magnetic flux of this solenoid is equal to the flux linked with each turn into total number of turns. So flux phi is equal to mu 0 Nia. This is the flux of a single turn into total number of turns. Total number of turns is equal to number of turns per unit length into L. N into L. So this is the total flux of this coil. And so flux phi is equal to, rearrange this equation, mu 0 N into N square A L into I. Or we know that the flux of any coil can be written as its self-inductance into current passing through that coil. Flux phi is equal to L into I. From equation 1, flux is equal to mu 0 N square A L into I. From equation 2, flux is equal to L into I. Compare these two equations. We have, by comparing equation 1 and 2, we can write L is equal to mu 0 N square A into N. L is equal to mu 0 N square A into N. So that's the self-inductance of this solenoid. The N is equal to mu 0 N square A into N. And we can write in another form, if capital N is the total number of turns, we can write L is equal to mu 0 into, instead of small letter n, we can write this equation in terms of capital N. Mu 0 n is equal to, we are writing like this way, n is equal to capital N divided by L. Substitute that, mu 0 n square L square A into N. L and L cancelled. So we write L is equal to mu 0 N square A divided by L. This is the expression of the self-inductance of the solenoid in terms of total number of turns, and this is in terms of number of turns per unit length. Suppose if you are inserting a rod of high permeability inside the solenoid, or these wires are wound over a material of high relative permeability. Suppose we taking a rod and our solenoid is wound on this rod. Suppose mu r is the relative permeability of our rod, then we can write the self-inductance of this solenoid is equal to L is equal to mu 0 into mu r into n square A divided by n. You know that mu r is the relative permeability of that rod. Since it is a good magnetic material, the mu r is very high. So the self-inductance of a solenoid can be increased by wounding the solenoid on a material having high relative permeability. Or we can rewrite like this way: mu 0 into mu r into, instead of capital N, if you are using small letter n, that is number of turns per unit length, n square A into L. That is the expression for the self-inductance of a solenoid where a core is inserted inside the solenoid. This is the expression for a air cooled solenoid, and this is the expression for a solenoid with a material core. Now let us see what is this phenomenon of mutual induction. It is the phenomenon of production of induced EMF in one coil due to a change of current in the neighboring coil. It is the phenomenon of production of induced EMF in one coil due to a change of current in the neighboring coil. To understand this concept of mutual induction, let us see an arrangement. Here we have two coils, primary coil and secondary coil, which are placed very close to each other. The primary coil is connected in series with a battery, tab key and a rheostat. And in secondary coil, we connected a galvanometer. Now suppose if you are just pressing this tab key, that we are closing the switch, a current start flowing through this primary coil. So a magnetic field is developed in this primary coil. The secondary coil is in the magnetic field of primary coil. We know that when we are closing the switch, initially the magnetic flux of the primary coil is increases because initially no current passing through this coil, no magnetic field. So magnetic field is increases when current start flowing through the circuit. So otherwise we can say our secondary coil is placed very close to the primary coil. So it is in a varying magnetic field. Because the secondary coil is in a varying magnetic field of primary coil because they are placed very close to each other. So what happened? The magnetic flux associated with the secondary coil also changes, and an induced EMF and an induced current is developing in the secondary coil. So you can observe that when you are closing this key, there is a momentary deflection in this galvanometer. There is a momentary deflection in the galvanometer when you are closing this key. But if you are pressing this key for a long time, that is, if you are closing this switch for a long time, we cannot observe any deflection in the galvanometer. The reason is that when the current is continuously passing, there is no variation of current, then we cannot observe any changes in magnetic flux of primary. Then there is no change in magnetic flux of the secondary, then no deflection. But if you are opening the switch, if you are releasing the tab key, again we can say the current in the primary coil decreases, the magnetic flux of the primary coil decreases, or otherwise we can say the secondary coil is in a decreasing magnetic flux. So again an opposing EMF is developing in the secondary coil, and an induced EMF or an induced current is developing in the secondary coil. Again we can see a deflection in the galvanometer, a momentary deflection when we are just releasing this key. So when the secondary coil is very close to a time varying, very close to a primary coil where a time varying current is passing to the primary, there is a production of EMF and current in the neighboring coil, and this phenomenon we can call as the mutual induction. The phenomenon of production of induced EMF in one coil due to a change of current in the neighboring coil. Now let us find what is the coefficient of mutual inductance. The magnetic flux of the secondary coil is directly proportional to current in the primary coil. The magnetic flux of the secondary coil is directly proportional to current passing through the primary coil because the secondary coil is in the magnetic field of primary coil. So the writing phi is proportional to I. The flux of the secondary coil is directly proportional to current in the primary coil. Phi is equal to M into I. And here the proportionality constant M is known as mutual inductance or coefficient of mutual induction. Mutual inductance or coefficient of mutual induction. Let us see a definition for that coefficient. If I is equal to 1 ampere, suppose 1 ampere current is passing through this primary coil. Then substitute for I equal to 1 ampere, phi is equal to M. Phi is equal to M. So the mutual inductance of two coil is numerically equal to the flux linked with the one coil when a unit current passes through the other coil. When unit current is passing through the primary coil, we can say it is the flux associated with the secondary coil. The mutual inductance is equal to the flux associated with the secondary coil when 1 ampere current is passing through the primary coil. That is the definition of mutual inductance. So in another way, we can write the induced EMF E is equal to minus d phi by dt. By Faraday's law, E equal to minus d phi by dt. Substitute for phi, phi is equal to m into I, so minus m into di by dt. And suppose if di by dt is equal to 1, so we can write E equal to minus m. So another definition for the mutual inductance. Mutual inductance is numerically equal to the induced EMF when the mutual inductance of two coils may be defined as the induced EMF set up in one coil when a current in the neighboring coil changes at a unit rate. If current in the primary coil is changes at a rate of 1 ampere per second at a unit rate, then we can define this mutual inductance as the induced EMF produced in the secondary coil. The mutual inductance of two coils may be defined as the induced EMF set up in one coil when current in the neighboring coil changes at a unit rate. That is, if you are putting di by dt is equal to 1, that is current changes at a rate of 1 ampere in 1 second, induced EMF in the secondary will be equal to the mutual inductance. Now let's see what is the SI unit of mutual inductance. The mutual inductance we are writing as M is equal to E by di by dt. So the SI unit of mutual inductance is equal to the SI unit of EMF divided by SI unit of di by dt. 1 ampere per second, 1 volt. So we can rewrite like this way: 1 volt second ampere raised to minus 1. And it is numerically equal to 1 Henry. 1 volt second ampere raised to minus 1 is known as 1 Henry and it is denoted by a symbol capital H. So the mutual inductance of two coils is said to be 1 Henry if an induced EMF of 1 volt set up in one coil when the current in the neighboring coil changes at the rate of 1 ampere per second. That's another definition for the Henry. The mutual inductance of two coils is said to be 1 Henry if an induced EMF of 1 volt set up in one coil when the current in the neighboring coil changes at the rate of 1 ampere per second. So the mutual inductance of two coils is said to be 1 Henry if an induced EMF of 1 volt set up in one coil when the current in the neighboring coil changes at the rate of 1 ampere per second. Now let us find the mutual inductance of two long solenoid. The mutual inductance between two long solenoid. Here we have two long coaxial solenoid. That is, the solenoid S2 is wound over S1. Two long coaxial solenoid S1 and S2 in such a way that S2 is wound over S1. So the length of this each solenoid is L. L is the length of each solenoid, but the radius and area cross section are different. Let's say R1 and R2 are the radii of two solenoid. That is, R1 is the radius of inner solenoid, that is S1, and R2 is the radius of outer solenoid. A, we are taking A is equal to pi R1 square is the area cross section of inner solenoid S1. Or otherwise we can say that's the common area, that's inner solenoid area is considered as a common area, that is A is equal to pi R1 square. The reason is that once you are calculating the flux of the second solenoid, even for S2, we can consider only the inner area, because the magnetic field of the inner solenoid associate with the outer solenoid only for an area A, because in the outer side of S1 there is no magnetic field. We know that. What is the property of the magnetic field produced by a solenoid? So once you are calculating the magnetic flux of the outer solenoid, we can take only the inner area. That's why we take in this common area. A is equal to pi R1 square, area cross section of the inner solenoid S1. Now suppose a time varying current I2 is passes through the outer solenoid, that is S2. We can call it a secondary solenoid and primary solenoid. It's primary coil, that's inner coil S1, and secondary coil S2, the outer solenoid. Suppose a time varying current I2 is passed through the S2. So it produces a magnetic field. We can say the magnetic field produced by the outer solenoid is equal to B2 is equal to mu 0 into N2 into I2. You know the magnetic field produced by a solenoid is equal to mu 0 Ni. So the magnetic field produced by the solenoid S2 is mu 0 into N2 into I2. We can rewrite like this way: mu 0 into N2, the turns per unit length, is writing in terms of capital N, the total number of turns, N2 by L into I2. Now, what is the magnetic flux associated with S1? You know, the S1 is inside the S2. So, the entire the magnetic field will produce the flux in S1. So, the magnetic flux, total magnetic flux linked with the S1 is equal to, we are writing it as phi 1. Phi 1 is equal to magnetic field into the magnetic field inside the S2, that is B2, into area cross section of the inner solenoid into total number of turns of S1. We are calculating what is the flux associated with the S1. That's why phi 1 is equal to B2. You know that S1 is in a magnetic field of S2. That is B2 into A into N1. Substitute for B2. B2 is mu 0 into N2 into I2. A into N1. So the mutual inductance of the coil 1 with respect to coil 2 can be write as the mutual inductance of coil 1 with respect to coil 2 can be write as M12. We are writing is mutual inductance of coil 1 with respect to coil 2. We already learned that the mutual inductance is equal to flux by current, phi 1 divided by I2. Phi 1 divided by I2. So in this equation, mu 0 N2 I2 is getting cancelled. We are dividing by I2. Mu 0 N2 A into N1. This equation can also write in terms of capital N, total number of turns in each solenoid, as mu 0 N1 N2 A divided by N. Mu 0 N1 N2 A divided by N. So that's the mutual inductance of coil 1 with respect to coil 2. Mu 0 N1 N2 A divided by N. Now think in another way. That is, suppose we are passing a time varying current I1 through S1. We are passing a time varying current I1 through S1. So inside the S1 we have a magnetic field that is given by B1. B1 is equal to mu 0 into N1 into I1. Mu 0 into N1 into I1. So we can also write as mu 0 N1 I1 divided by L. So the total magnetic flux linked with S2. Remember, once you are calculating what is the flux through S2, S2 is the outer coil, but this magnetic flux is only for an area A, that is inner area, pi R1 square. Once you are calculating the flux of the secondary coil, even for S2, we can use only the inner area. The reason is that outside the S1, there is no magnetic field. So we can only use the inner area. That's why the total magnetic flux linked with S2 is equal to, that's writing as phi 2. Phi 2 is equal to B1 into inner area into N2. This is actually the area of inner solenoid S1 by R1 square. Or otherwise can consider as a common area. B1 A into N2. So mu 0 into, substitute for B1, mu 0 N1 I1, that's B1, A into N2. Or the mutual inductance of coil 2 with respect to coil 1 can be write as M21 is equal to Phi2 divided by I1. So dividing by I1, we will get mu 0 N1 N2 into A. Or this equation can also rearrange. M12 is equal to mu 0. We are writing N1 is equal to capital N1 by N. Mu 0 N1 N2 A divided by N. What's our conclusion is that the M12 is equal to M21. That is, this is M21. That is, M12 is numerically equal to M21 because we're getting M12 is mu 0 N1 N2 A divided by L, and M21 also mu 0 N1 N2 A divided by L. So M12 is equal to M21 is equal to M. Or commonly we can write as mutual inductance between these two coils is equal to mu 0 N1 N2 A divided by N. Or mu 0 in terms of small letter n, number of turns per unit length, mu 0 N1 N2 A into N. So the mutual inductance of two coils is the property of their combination. It does not matter which one of them function as primary or secondary coil. Once we are passing the current through the primary or secondary coil, it does not matter. The mutual inductance actually is the property of combination. The mutual inductance of two coils is a property of their combination. It does not matter which one of them function as primary or secondary coil. That's why we're getting as M12. The mutual inductance between the primary coil and secondary coil is same when we are passing the current through S1 or S2. M12 is equal to M21 is equal to M. That's about mutual inductance. That's all today. Thank you.